Okay, in chapter 6, we're going to kind of extend Newton's laws that we use in chapters 4 and 5 and apply them with some circular motion stuff that we learned in chapter 3 in order to get some kind of the forces involved in circular motion. And we'll also talk about gravitation, Newton's law of gravitation. So the goals are, we're going to understand the dynamics of circular motion. Like I just said, we've talked about in chapter 3 the kind of the radial acceleration or the centripetal acceleration that an object has when it's in uniform circular motion. And now we'll talk about the causes of that and the dynamics of that. And so Newton's second law of that. We'll also, talk about Newton's law of gravitation. We'll talk about weight and mass and relate it to Newton's law of gravitation. I know in the past, we were looking back at the chapter 4 material. We were talking about action-reaction pairs. There was an apple and there was a force of the earth on the apple. And the reaction to that was the force of the apple on the earth. And this is where we'll look at where that force comes from and how that fits into the kind of Newton's law of gravitation altogether. And then we'll also talk about the motion of objects. So we'll talk about uniform circular motion and gravitation as kind of the cause of that uniform circular motion, which is orbit. So the first thing we need to do is we need to review a little bit about centripetal acceleration, which you remember from chapter 3. So we have here an object in uniform circular motion. It's traveling in a counterclockwise manner, and we say it's circular motion because it's going in a circle, and it's uniform because it's the speed or the magnitude of the velocity is constant throughout. The only thing that's changing with it is the direction, right? It's always the same magnitude of the velocity. So we remember back, so we see here, our velocity vector here is to the left, here it's down to the left, down to the right, strictly to the right, up and to the right, up and to the left, etc., right? And we had, if you remember back from chapter 3, we have a radial acceleration. And this radial acceleration is always directed perpendicular to the instantaneous velocity vector, right? The reason that the radial acceleration is perpendicular is so that it causes only a change in the velocity vector. If we did not have it perpendicular, if we had anything other than perpendicular, then it would change the speed as well, right? If I had it parallel, it would change only the speed and not the direction. If I have it perpendicular, it changes only the direction and not the speed, and anything in between would cause a change in both, right? So in order to have uniform speed throughout, we need to have the radial acceleration always be perpendicular to the velocity vector, right? So here's our radial acceleration, and it's always directed towards the center, right? Because it's always bending towards the center. If this velocity went off like this, if I didn't have any more acceleration towards the center, it would just continue off like that. But that's not what it's doing. It's sort of moving towards the center all the time. So by the time between here and here, it's curved in like this, and that's due to the radial acceleration. Now, we said that we sort of derived the equation for the magnitude of the radial acceleration, and we said that this is equal to the velocity squared divided by the radius r. So this is our radius r, and then the velocity is this, and it ends up being the speed squared, right? You square a vector, it becomes a scalar. And this is equal to 4 pi squared times the radius divided by the period squared. This is a result of the fact that the velocity is 2 pi r divided by the time. This is the circumference. So the distance it travels divided by the time it takes for traveling. So t is defined as the period, which is the time for one revolution. 2 pi r would be the distance it travels, and one revolution is the circumference, or r is the radius. So just a little review of centripetal acceleration there. So how does centripetal acceleration or radial acceleration, those are the same thing, compare with Newton's second law, F equals ma? Well, radial acceleration is an acceleration, right? And we have Newton's second law relates a force to acceleration, so there must be a relationship between a force and your radial acceleration, right? So we know that from Newton's second law, we have F equals ma, so we can find the net inward radial force on an object, right? If we have an acceleration toward inward, right? That's the radial acceleration. And so we can also find a radial force inward. So we say the net force must be equal to mass times the radial acceleration, right? This is just Newton's second law, in which I've replaced the acceleration with radial acceleration, just a specific type of acceleration, but it's the same law. So this is also equal to mass times, since radial acceleration, this is equal to v squared over r, we say that the net force is mv squared over r. This is often referred to as the centripetal force, which means center seeking. This is I think Latin, maybe Greek or Latin, I think it's Latin, for center seeking. It's a center seeking force. But it's not really a force. It's not a real force, and it's not something that we would include in our summation of forces. It's simply a requirement. Remember, the velocity squared over r, if you look back at chapter 3 stuff, that was a requirement for the object to stay in that motion, that particular motion. So the centripetal force isn't really a force. At least the velocity squared over r is not a real force. We have other forces that cause that centripetal motion, or that uniform circular motion. So this is a requirement for the object to stay in this. It's never ever included in the summation of forces. So if it's not included in the summation of forces, it always goes on the right hand side over here. It's always in the a radial, the ma, right, or the mv squared over r. It's always on that side of the equation. So, you know, like I was just saying, the centripetal force isn't somehow generated by the motion of the object. I don't have an object in a circle that generates an inward force. That doesn't really make any sense to say, oh, it's traveling in a circle, so it must be creating a force inward. That doesn't work. What we need to say is that we have something traveling in a circle because it's acted on by a force, right? The reason for its motion, the reason for it to be in a circle, is because there's a force acting on it to pull it in towards the center. And it's that radial acceleration, so it's that radial force or centripetal force, that center-seeking force. It means going towards the center. It's always trying to turn in towards the center, right? So if I have some radial force, it causes some radial acceleration, and it causes it to bend towards the center. So as this travels off like this, then it bends towards the center. It's continually bending towards the center, right? And bending towards the center. And then let's say the string were to break, right? So if the string breaks, then obviously there's no more tension in the string, right? So the force would disappear. And what happens if the force disappears? The acceleration towards the center disappears, right? So if the acceleration towards the center disappears, then we have no more acceleration. And acceleration is a change in velocity, so we have no more change in velocity. So if the string breaks, then it would just continue off in the velocity, or with the velocity it was going, in the direction it was going with the same speed that it had. Okay, so If we lose that force, then we lose that acceleration, and velocity remain constant when that happens. So let's just look at a really simple example of this, very similar to one we did in chapter 3. And again, look through the example video in Mastering Physics for the full solution. I just have the answers here, but I'll talk about how to set it up. So we have this this airplane that's going to be going around in this counterclockwise circle right here, and it's on a string, and it is because it just flies forward. It's on a propeller. It tries to fly forward, but it's on a string, so we're actually going to pull it to keep it from flying forward. It wants to go that way, but we're just going to accelerate it this way constantly. And our string is 5 meters long, and so the question is, what is the tension in the string, right? So we can actually find the tension in the string just by knowing how fast it's going to fly, or actually how long it takes to go around, and the radius, right? So it makes a revolution every 4 seconds, so that would be our period t. It's on a 5 meter string, so that's a radius r, and it also has a mass of a half kilogram. We'll need that in order to get our F equals ma, right? We need to know how much the plane weighs. So if we could find the velocity from 2 pi r over the time it takes. So 2 pi r would leave us with 10 pi divided by the time it takes is 4 seconds, right? So 2.5 pi would end up being our velocity. So that's 7.85 meters per second, right? Radius was in meters, time or period was in seconds, so 7.85 meters per second. And then our centripetal acceleration, or our radial acceleration, is velocity squared divided by the radius. So 7.85 squared divided by 5 leaves us with the centripetal acceleration, or the radial acceleration, which ends up being 12.3 meters per second squared. So then in order to find the tension, I know that I can draw a free body diagram of this plane right here, right? And it has a weight lifting, pulling down on it. Obviously, there's a gravitational attraction there. But what they don't say in here, it's flying horizontally. So the reason it's horizontal is it actually has a lift, the airplane lift, that equals its gravity. So we're only dealing with one dimension right here. They don't say that here, but the lift from the plane is balanced out by the gravity, or vice versa, however you want to look at it. So we just have, we can draw a free body diagram with both of those, and they would cancel, and we would just have some force to the left, right, or force inward. And this is where I've mentioned that we might want to sometimes call to the left on our positive direction. We practice around with changing our coordinate systems a little bit. And this is one case we might want to do this. You might want to just call this a positive force. So we have a radial acceleration equal to 12.3 meters per second squared, and the mass is a half kilogram. So if we want to find the force, it's simply a half kilogram times this radial acceleration. So ends up being 6.15 newtons is the tension. And again, look through example 6.1. Now, of course, we don't have to make problems so simple that they're in one dimension. We can solve problems in 2 dimensions as well, right? Well, this is a really good one here. We have a tether ball. This is example 6.2. And again, I encourage you guys to, after I explain the general principles behind this, try to solve it yourself, and then watch the video on Mastering Physics. But what we have here is we have this tether ball that is going around in a circle, and it, as it will say it's a perfect circle and it's in uniform circular motion down here. And it travels at some radius r off of some vertical axis here. And now it's not that we have gravity balancing or like a gravity balancing like the weight of a lift or the force of a lift or anything like we had in the previous problem, but now we have this string which is going to have to balance it out in the vertical direction, right? So if I were just to look at the ball here in one snapshot of time, I could draw a free body diagram of this, right? So I draw the ball right here and I'd say, all right, we have a weight acting down, obviously mass times gravity acting down, and then I have a tension force acting on it. And these are the only two forces acting on it, right? So they are the only two that I am going to put into my free body diagram as far as touching the object that I'm free body diagramming, the ball here, right? But I know we always have to ask what is going on physically, right? And we know that if it's in uniform circular motion, then it's accelerating. It has to be accelerating, and it has to be accelerating inwardly. So I drew the ball here when it was off to the right side of the circle. It needs to be accelerating back towards the center. So I draw my radial acceleration off to the left here. So setting up the free body diagram here. And then after this, it becomes very much like a chapter 5 problem, in which I would want to break this tension into its vertical and its horizontal components, right? Same thing we've been doing since chapter 1, right? So I have, now again, just like last chapter, we have to be careful. If this angle beta is given off the vertical, then it changes their sine and cosine, right? So the y component would be this force of tension, Ft, force of the tension times the cosine of beta would be our y direction. And in the x direction, the force of the tension times the sine of beta is the direction off here, right? So I've gotten rid of this. That's what the squiggly line means. We've gotten rid of the tension force there and turn it into a vertical and a horizontal component. And I have my weight here as well, right? And then we just do a summation of forces. We ask ourselves, so is accelerating inwardly, is it accelerating vertically? And hopefully we say no, right? It's sitting there just going around in a circle in the same horizontal plane here. So we say that the tension force times the cosine of beta is equal to the weight, right? So we can actually, if we're given a mass of the ball, we can find out, and we're given a beta, we can find out what the tension force is. And then with the tension force found, I can find the force that is accelerating it towards the center, right? Which can give us a, if I know this force, I can say F equals ma, and I can find the radial acceleration. Or really we can solve for anything. So the example asks us to derive equations for the tension force and the angle beta. So we have a bunch of equations. We have Ft is equal to mg, and we have our Ft cosine beta equals mg, and Ft sine beta equals ma radial, which is equal to mv squared over r. And actually we can find r in terms of L if we wanted to. We can say that r is going to be equal to L times the sine of beta. So there's a lot of algebraic relationships we can develop here, and I encourage you to try to develop as many of these relationships and work with doing Newton's second law with the uniform circular motion as much as you can to get familiar with the kind of the process of it. And then when you plug in the numbers, it's much easier to solve. So there's a lot of real life situations that use forces that will cause centripetal acceleration going in a circle. And it doesn't necessarily have to always be going in a circle. It's not like I can only solve problems that are continually going around in a circle. I could consider a car going on a freeway that goes around a curve. Well, if that curve is circular, if I can get a radius of that curve, then for a moment that car is in uniform circular motion, and I can use these concepts to solve for that moment while the car is going around the curve. So I can figure out things like how much would I need to bank a curve, especially if we add in friction and stuff. Let's say I'm building a highway in Minnesota and I expect it to be icy, so there's no coefficient of friction. I might want to bank the curve around a certain curve so that the car doesn't slide off, right? So there's a lot of applications for it. I can have a level curve in which we're just, maybe we're driving around a curve on a flat ground, a bank curve like the one I was just discussing, maybe in Minnesota or something, and then horizontal circles. So just something like the plane example we had a minute ago, or something is just flying around in a horizontal circle. And we can also turn this around and do this in vertical circles as well. So I can, like a Ferris wheel or something like that. So talk about at the fair. So we have horizontal circle, here's your merry-go-round, and vertical circle, here's your Ferris wheel. So those applications as well. So let's take a look at some of those. Okay, so let's take a look at one of the examples, a banked curve. So we'll do problem 6.8, which is similar to example 6.4. So I would recommend pausing this and then go run through example 6.4 and then come back and we can work on this one, or try this one, and then we'll see if we can get the same solution there. So we have a highway curve with a 900-foot radius, and it's going to be banked so that a car traveling 55 miles per hour won't skid sideways, even in the absence of friction. So, if we have like an icy roadway somewhere, we want to make sure that the car is not going to skid when it goes around this curve. So make a free-body diagram and find the angle that it should be banked. Well, the first thing we want to do is we're given 55 miles per hour, right? And we have gravity, and English units is 32 feet per second squared, and so we need that in feet per second. Needs to be our unit, so we need to convert miles per hour to feet per second. So 55 miles an hour is 80.7 feet per second. And then the next thing is we need to kind of sketch up what's going on here. So it's banked at some angle beta. So it's some angle off the horizontal, some angle beta here, right? So it's inclined up here, beta, so the car is going around, and like here's the ground here, and it's kind of going in the circle here, so it's going around that curve. Like a racetrack have banked turns a lot. So this is the car. Obviously, it's going to have a weight that goes straight down, right? And it needs to have, in order to stay going in this curve, this highway curve for however long it's in there, it needs to be accelerating towards the center, right? I need to have something to cause some acceleration towards the center so that it turns towards the center. And the magnitude of that acceleration needs to be v squared over r. It needs to be my radial acceleration, right? So just kind of drawing these angles here. This is beta. Then we'd have the vertical angle here. Opposite of it is beta. Then if I have my normal force coming out, right, because normal is perpendicular, then this is, that's perpendicular there. This is perpendicular here. This is 90 minus beta. So then this angle right here left over would be beta, right? So it's measured some angle beta off the vertical, right? I could say it's beta degrees off the vertical is my normal force. So then doing this, we see that the component, and it's the normal force that causes it, right? There's no other force obviously my weight isn't causing an acceleration that way, right? The weight of the car is strictly down. I need something to cause some force or something to cause acceleration this direction, right? So the only thing that even has a component in that direction is the normal force. So the normal force is causing, it works as our centripetal force. It causes the centripetal acceleration. And so the component of this would be normal force times this would be the sine of beta, right? This is beta here, then this would be normal sine of beta. So we have here the normal times the sine of beta has to be equal to mass times our radial acceleration, mv squared over r. And we also have, we know that the normal force has some component that's up as well, right? It has some component up here, some vertical. So that's what we're going to use to balance out the weight, because it's not accelerating into the curve at all, right? So we have to say that this one is in cosine beta, right? So the normal force times cosine beta, that's going to have to be equal to our weight. So we have n cosine beta is equal to the weight, or mg. So we can actually combine these together. We could use this solution every single time that we go through and solve a problem like this, or we can actually combine them together. If I take this first one, sine beta, and then take this equation divided by this equation, so sine beta divided by cosine beta will leave us in n sine beta divided by n cosine beta. And I don't have the work up here. I might try to write this out and put it up later, but if not, we'll do this one in class. But we have n sine beta divided by n cosine beta would leave us with tangent beta, and mv squared over r divided by mg is going to leave us with just v squared over rg or gr. So we have the tangent of beta ends up being the velocity squared divided by acceleration due to gravity and times the radius of the curve, right? The radius, maybe that's from here to here if it's going around a horizontal circle. So we can just use this fact to find beta, right? Well, I'll just simply take the arctangent, right? If arctan of tangent of beta is just beta, so we'll just take the arctangent of v squared over gr. We have velocity, we have g, and we have r is 900 feet. And so we end up with a beta of 12.7 degrees. So for a car traveling at 55 miles an hour around a highway curve of 900 feet, if we can bank it at 12.7 degrees, then we won't need any friction in order to keep us from sliding up or down on here. Okay, another type of uniform circular motion in dynamics is a vertical circle, right? Which is pretty much no different than a horizontal circle. It's actually exactly the same as having something in a horizontal circle like we had the plane, but gravity will play a much different role when we have something in a vertical circle. So we just need to be careful how we treat weight and how we treat gravity, because gravity can actually act as the centripetal force, right? The thing that gives us the uniform circular motion. So we got to make sure to use free body diagrams. Be careful. So here's a sort of conceptual thing. Maybe if you've ridden on a Ferris wheel before, you probably have noticed that you feel lighter in one place and you feel heavier in one place, right? And so it's sort of similar to when you're riding in an elevator and you feel lighter and heavier. When you're on, it's actually pretty much the same thing when you're in an elevator. When you are, where do you feel lighter when you're on a Ferris wheel? Is it one of the sides, or is it the top, or is it the bottom? and it's most likely that you feel, you should feel that you're lightest at the top, right? And then where would you feel heaviest? You feel heaviest actually at the bottom. And the reason for this is that we have here our acceleration sort of changes, right? It's not really constant acceleration. It's constantly inward, but the direction of it isn't always the same. Now, if I were to free body diagram myself at the top, I have a weight pulling down, and I also have an acceleration down, right? I have a weight down, and I have to have something causing some acceleration downwards. Okay, and this guy's going around in a clockwise direction, so there's velocity here, velocity there, which the direction doesn't really matter as far as his acceleration goes, his radial acceleration. So at the top, he has a weight down, and he must be accelerated down, which kind of works out nicely because weight is down, and he needs to be pulled down. Well, at the bottom, he has a weight that's down, because weight is always down, but he needs an acceleration upwards, right? So there's a weight pulling him down, but somehow he needs to be accelerated upwards. So the other force we have here is he's sitting on a seat, right? In both cases, he's sitting on a seat. So there's a normal force. So if I draw the free body diagrams, we have he has a weight down and he has a normal force at the top. We'll call it NT, normal force at the top. And the sum of these needs to result in some acceleration downwards, right? So they need to equal, this minus this has to equal, negative this, right? It needs to be going downwards, right? So we have the acceleration that's needed is the same direction as the weight. So I don't need as much of a normal force here. I need, basically, think of it, if I were to call positive y down, I could think of my weight minus the normal force gives me my centripetal force required for this acceleration. So I'm at the top, gravity is actually acting as my centripetal acceleration. Versus at the bottom, I have a weight down here and I have a normal force up, and now I need an acceleration upwards, right? So now gravity is actually opposing the acceleration that I need. So I need a greater normal force because I need my normal force minus my weight to equal my my centripetal force. So I need a much greater normal force in order to get my acceleration. And the difference here is basically I'm subtracting gravity here or I'm adding gravity here, basically. This normal force needs to be acceleration or centripetal force plus gravity here, and here my normal force needs to be my acceleration minus gravity, okay? So if I were accelerating in, if v squared over r was equal to 9.8 meters per second squared, then my normal force at the top would be 0 because that's exactly what gravity is giving me. So I don't need any sort of normal force whatsoever, right? If this needs to be 9.8 meters per second squared and this is 9.8 meters per second squared, then this would be 0. Conversely, if we need an acceleration upwards at 9.8 meters per second squared, then I need this normal force to be twice my weight, right? I would need this to be equal to 2 mg. So 2 mg minus mg would give me my acceleration upwards. We'll run through a bunch of examples, but there's some equations. Sorry, my microphone's getting messed up. So there's some equations we can run through or equations we can derive that'll make it easier to deal with these. So like a loop-the-loop is one, it's just like a Ferris wheel, right? It's the same thing where the guy is going around in a circle. You have a pilot going around in a circle. So it's in a vertical circle. At the bottom of the loop, the upward force experienced by the object is greater than the weight, right? And I'll run through this derivation more in class, but it ends up being, this is my radial acceleration, right? And I said in the last slide, there was a matter of adding weight plus radial acceleration. So I can factor out the weight, and the normal force at the bottom ends up being the mg times 1 plus mv squared over r. The g's would cancel here. So it ends up being weight plus mass times radial acceleration. I don't have this derivation in this presentation, but run through, you can kind of reversely derive it. Go backwards from this and see that it works from the free body diagram, or draw the free body diagram and derive this on your own. That's actually a really good practice. Better than waiting for me to do it in class. On the other way, if he's at the top, then we have gravity is working down, right? And I need some acceleration downwards, right? So at the top of the loop, the object is less than the weight, and so this is equal to the acceleration required minus gravity, right? So mg times v squared over rg, the g's would cancel in this one, so we get mv squared over r minus mg, the centripetal force minus the weight at the top, right? Minus whatever gravity is helping us out with. So again, go through and derive these at the top and the bottom of the loop. Okay, now moving into Newton's law of gravitation. Newton's law of gravitation basically says that every piece of matter, mass, is attracted to every other piece of matter. And the magnitude of that force is proportional to the product of the masses of the two objects, and inversely proportional to the square of the distance between them. I'll put the equation up on the next slide here. But Newton's law of gravitation, or sometimes thought of as the universal law of gravitation, says everything is attracted to each other. This law, the force is always an attractive force, so it's always pulling together. And in order to actually really have a force that's even close to humanly perceptible, you need very large masses, because it's equal to the product, and they also need to be pretty close together, right? So or can't be too far away. Anyways, the equation I'll bring up on the next slide here. So this is what Newton's law of gravitation says. Basically, is you have mass 1 right here, and you have a mass 2 right here, different masses, and you have a attraction force between them. Okay, so they're separated by some distance r. This is not a radius, it's just simply a distance r. This is the distance between the two of them. So it's not like you would find the distance between the two and cut it in half. It's just the distance between them, and we use r instead of d. So Fg is this gravitational force. Generally, instead of just using g we use g for the acceleration of gravity, and Fg for the gravitational force between two objects. So the equation states that the gravitational force between two objects is directly proportional to the product of the masses, so mass 1 times mass 2, and inversely proportional to the square of the distance between them. So m1, m2 over r squared, and then we multiply by some constant of proportionality here, which we call a gravitational constant, g. So F, the gravitational force between two objects, is the gravitational constant times the product of the two masses divided by the square of the distance between them. It's important to note that Fg here is the same as Fg here. It's the same magnitude of force, and this one the force of gravity would would make M1 move to the right, it would make M2 move to the left. It would make them move towards each other as an attractive force. So the gravitational constant here is very small, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. You can see that, if you multiply by this gravitational constant, you have meters squared on the top, you'll have meters squared on the bottom here, and you have kilograms squared on the bottom, kilograms squared on the top, so you're left with just newtons. So the force is in newtons. So this is a very small gravitational constant, and so that's why we need very large masses in order to actually even have something that's humanly perceptible, right? Have something that's like 10 to the 5th and 10 to the 3rd or something like that, then you'll start getting, some forces that are perceptible if they're close together. So this might not seem altogether obvious that any two masses attract each other. So in 1798, Henry Cavendish came up with this experiment to sort of tested it, but it also gave a way to measure the value of G, the gravitational constant. So basically, this experiment has some mass over here. That's M2. This is the large mass. They're the same masses, right? And then there's some small mass, M1, same masses here, and just kind of put them on these rods next to each other. So you have a plate here that the big masses sit on, and then the small masses sit on this other little bar right here. And they sit at some distance away, right? And then up on here, this is a quartz fiber rod, so it rotates, it can twist. And then they put a mirror up here, right? At the top of the quartz fiber rod. So then this attraction between these two masses causes this rod to twist, right? So it twists around, and before the masses are put on there, there's the laser can shoot the mirror, and then it'll come back to read a scale here. Because it doesn't twist very far, right? It only twists a very small amount. So in order to measure how far it twists, they have a laser shoots here, and then after they can measure where it shot to before putting the mass on, and then putting the mass on causes it to twist, and it causes the laser beam to shoot back out at a different reflect back at a different location, and then you can measure the distance between here, and this distance here, so you can get an angle, right? And so after you have the angle at which it rotated through, you can work backwards and find the distance and find the force, and eventually get the gravitational constant G. But interesting experiment. So you put these the balls here together, and then they're attracted, and so they would twist this rod and change the reflection point of the. Okay, let's do a quick example here with Newton's law of gravitation. We'll do this one in class too, but basically this is problem 6.18, rendezvous in space. So basically we have two astronauts that are going to try to meet via gravitational attraction. One of them weighs 65 kilograms, one of them weighs 72 kilograms, and they start 20 meters apart, right? So this would be our distance apart is 20 meters. This is mass 1, this is mass 2. We make a free body diagram of each astronaut, then they would simply have there wouldn't be any, if they're in space, they wouldn't have any gravitational attraction from Earth, just because the distance is so far. They would just have a gravitational attraction between them, and they wouldn't have a normal force because they're not saying anything. It would simply be they would have a force pulling towards each other. And we're going to use that to find their initial acceleration. So we can find their gravitational attraction force is just 65 times 72 times g divided by 20 squared, and we can get their the force of attraction between them. And then we know the mass of each one, right? So we have a force divided by mass would be their acceleration. So each of them will have a slightly different acceleration, right? They'll have the same force, but they'll have different accelerations because they have different masses. So we can find out their acceleration, and then if their acceleration remains constant, we can go back to chapter 2 material and find the distance. We have a delta x they have to travel. We have an acceleration which is constant, and we can figure out the time from there, how long it would take, right? And part C, would their acceleration actually remain constant? And no, it wouldn't, right? Because as they get closer, then their gravitational attraction would actually increase, right? Because the gravitational force is divided by the distance between them squared. So as they get closer, what we're dividing by gets smaller. So take a look at this problem, try to work it out. It's a pretty straightforward problem, but we'll also run through it in class. And the answers are here. So the acceleration of astronaut A, one of the astronauts is 1.2 times 10 to the negative 11th meter per second squared, and astronaut B is 1.1 times 10 to the negative 11th. It'll take about 15 days, and like I said, no acceleration will not remain constant. Okay, there's some variations with gravity on Earth, as well as obviously if you're on a different planet, right? If I were on a smaller planet, or if I'm on the moon, then the mass of the moon is much less, right? So the gravitational attraction on the moon is also much less. And if I were on Jupiter, Jupiter is much more massive than the Earth, so the gravitational attraction force would be much more. This is why the acceleration due to gravity is like a fifth, or like 16% of what it is on Earth, on the moon, and on Jupiter it's many times more than what it is on Earth. But you get varying, even within the Earth itself, you get a variation of gravity because you have different densities within the Earth, right? And density is defined as, well, you see the units here, it's kilograms divided by cubic meter. So it's the amount of mass you have per some unit volume. So this is in thousands of kilograms per cubic meter. So you see the inner core is very dense, and your outer core is less dense, and then the mantle, and then the crust out here obviously is no density whatsoever, right? Because there's not much mass there. And so even within it, since the gravitational attraction force is proportional to the mass, if I have more mass, I'll have more gravity here, right? Yeah, so you get a variation of gravity within the Earth. Here's a picture of this, better illustrated. So you see that the red areas are where there's stronger gravity, and blue areas are where there is weaker gravity. And you see, I mean, it's not necessarily uniform. We have, the Andes Mountains are right here, very big mountain range, very high gravity right here, but it drops off there for some reason. And you see some increase through the Rockies, but it's not consistent. So it's not necessarily, doesn't necessarily have something to do with, there's more mass, or there's a big mountain, so there's more mass and more gravity, or anything like that. It plays some role in it, but the material can have effect as well if you have more dense materials, obviously. But not to get too far into this, you get some variations on the Earth itself. It can be it's roughly 9.8, but it can be anywhere from like 9.7 meters per second squared to 9.9 meters per second squared. So if you were to go, over here in the middle of the Atlantic, you would actually weigh less than if you're in Hawaii. Well, obviously, there's variations inside the Earth for the gravitational force. There's also quite a variation as you go away from the surface of the Earth or from the center of the Earth out this way. You see the equation for the force of gravity, gravitational force is, gravitational constant times mass of Earth, if we're on Earth, mass of Earth times mass of the astronaut divided by the distance between them squared, right? And this is the distance from center to center. We just assume we're going from the middle of one to the middle of the other. So, if we were near the center of the Earth, then, we would have increased acceleration because we're closer to the center, right? But on the surface, we have this. This is our radius, 6.38 times 10 to the 6 meters, and our weight, let's say the astronaut weighs 700 newtons here, right? Well, as he goes off further and further away, it falls off by the distance squared, right? Because we're dividing by the distance away squared. So when he goes to twice as far away, so he's at 6.38 times 10 to the 6. By the time he's at 12.8 times 10 to the 6 meters away right here, it's actually only a quarter of the force, right? Because twice the distance away would be 1/4 of the force, right? And if I went 3 times away, or 3 times as far away, then I would, divide this by 3 squared, so the force would be 1/9. So his weight would be 1/9. So it falls off very quickly as we leave Earth. We can use this fact, though, that gravity decreases the farther we get away, in combination with the fact that we need something to pull things back towards the center in order to have uniform circular motion. We can use both of those in order to actually put something into some uniform circular motion. So let's say let's say we have a tower here, maybe it's the Eiffel Tower or something, and we launch something off of it, and we launch it so that the effects of gravity pull it down to the Earth right away, because the acceleration, the radial acceleration, or actually gravity, is greater than the required radial acceleration in order to make this go in a circle, right? So gravity's pulling it down too much. If I launch it a little bit further, then it would travel further, right? Because it's going faster, so in the same amount of time, it would travel a little bit further, right? Well, if I were to launch it fast enough, then gravity pulls it back towards the center, but it's trying to shoot off like this. It's trying to shoot off towards these green lines, right? These green arrows. But so it's going away. It's trying to get away, but gravity keeps pulling it back, right? And it's going so fast that every second that gravity pulls it in a little bit, it goes a little bit further away. So it shoots out and gravity pulls it down, and gravity keeps pulling it down, but it actually never reaches it. And so it can end up in this orbit like this. Now, if it's not, exactly the right velocity, then we'll get some sort of like an oblong shape, or we'll actually get this elliptical shape, right? Where it gets really close over here and then it gets further away over there, because it's not, perfectly shot at the velocity that would give us the appropriate radial acceleration. It's actually getting a little bit closer and closer to Earth every time here, and then it kind of launches back out, and the combined effects of the reduced force of gravity and the speed give it this elliptical orbit. If we launched at exactly the right speed, though, where the velocity squared divided by the radius, it would be this radius. It would be from the path to the center, this radius right here. If that is exactly right, that b squared over r, if that's equal to the gravitational acceleration, the gravitational force here, which is going to be a little bit different. Remember, because our gravitational force is dependent on how far away we are. So the gravitational force would be a little bit different. But if it works out so that b squared over r gives us the same as the required. Sorry, if the centripetal force required, so mv squared over r, is the same as the gravitational attraction force we get here, g m1 m2 over r squared, then this will end up in a perfect circle. If that makes sense. And if we shoot it too fast, then it would, get back into an elliptical orbit again. We have some variations getting farther away here, closer there. And then if we launch it too fast, then the Earth can't accelerate it back, and then we call these the escape velocities, right? So anything above, maybe above 5 or 6, at least 6 and 7 are both escape velocities, right? Or escape velocity is actually the minimum velocity in order to escape the pull of the Earth's gravitational pull, or to get it far enough away so that it really doesn't have much of an effect anymore. So that finishes it up for chapter 6, but just like I did in chapter 5, I want to go through multiple choice problems, so let's do some. Okay, so if we have a stone of mass m attached to a string whirled in a vertical circle with a radius r, and then we want to know we're told that at the exact top of the path, the tension is 3 times the stone's weight. So what's the speed? So we're given the tension, we need to find the speed. Well, first thing we would want to do is draw a free body diagram when it's at the top, right? So in that free body diagram, you would have the object would be here, and you'd have a weight of it of mg, and then you also have a tension acting down as well, which is 3 mg. So when you sum these together, you have a downward force of 4 mg. And so since we're at the top, we have, if it's in a vertical circle, so we know at the top the radial acceleration is pointed straight down, right? So it's that 4 mg, the 3 mg that come from the tension and the 1 mg that comes from its weight. So we have 4 mg that causes the radial acceleration. It is the centripetal force. It causes the centripetal acceleration. So 4 mg is equal to 4 is equal to the centripetal force. So that's mv squared over r. So I'm sorry, I'm not writing this out on the screen. I'll do another video later with this, writing out this problem. But we have 4 mg is equal to 4 mg is equal to mv squared over r. And we want to solve this for velocity. So you can write this out as I'm going along. We have the m's would cancel out on both sides. So we have 4g is equal to v squared over r. So you can say solve for v, and you would get the square root of 4gr. Pull the 2 outside, and we would have the speed is 2 radical gr. In this problem, we have a rocket that's over the United States, and then the question is whether or not where would the bomb land if it's released when it's directly over the U.S.? Now, hopefully, at least just from the Chapter 3 material, you wouldn't say directly below on the United States, because if it's going around the Earth, then it has some velocity, right? So it would at least be, traveling horizontally while it's falling, at least, right? So hopefully you don't pick A. Other choices we have here is follow a curved path and most likely land in the ocean. It would not hit the U.S. because it would remain in orbit with the rocket, or it would move in a straight line out into space. Well, hopefully you wouldn't say D either, because we're just talking about gravitation, and we know that Earth is going to pull it back. The gravitational attraction of Earth is going to pull it towards the center, right? So it's not going to move in a straight line. So we know A and D aren't going to work. So we know it's not going to fall directly below because it's moving along, and it's not going to go in a straight line because it's being accelerated down. So it's actually, if it's traveling with the rocket that's in orbit, the rocket is exactly the right speed in order for its radial acceleration to exactly equal the gravitational attraction of the Earth. So it stays at the same distance away. It's in orbit. And if you were to release anything from that rocket, it would have that same speed and it would have that same gravitational attraction. So it would have the same path. So if they were to release a bomb from the rocket, then the bomb would just sit there right next to the rocket and actually blow the rocket up. So it would not hit the United States because it would remain in orbit with the rocket. So in this one, if we have a mass, the end of a bar, the end of a spoke of a wheel, and when the weight is at its lowest point, the tension is equal to 2W, or twice the weight. W is the weight, right? So the tension is 2W when it's at its lowest point. So when it's down here, the thing is, if it's in a vertical circle and it always accelerates in towards the center, then when it's at the bottom, remember it's more. The tension or the normal force would be more, right? Because it has to accelerate in towards the center with that radial acceleration. So we would need a tension to not only counterbalance the weight they would have down, but also to cause some acceleration towards the center. So since the tension is equal to 2W, then we know one of the W's is due to the weight, and then the other W must be due to the acceleration towards the center. So if we need tension equal to its weight in order to accelerate it to the center, we can say that the rate of the acceleration, or the radial acceleration, is actually has to be 9.8 meters per second squared as well. It must be equal to the acceleration due to gravity, right? Because it's exactly the same force. The tension, in order to make it accelerate towards the center, is the same as its weight. So the radial acceleration is g. So when we get up here at the top of its path, then it has a required radial acceleration, right? And we know that that radial acceleration required is g, right? It has to be pulled down at g, but fortunately it has a mass, and it has, some gravitational attraction of that mass. It has a weight. So gravity is already pulling it down at a rate of g. So we have gravity pulling it down, and we have a radial acceleration that has to be equal to gravity. So there needs to be no further tension in order to pull it down. So the tension here would be 0. There is no tension at the top. It's twice the tension, or twice the weight at the bottom, and no weight at all at the top. Remember, you look back to the equations we had with the Ferris wheel and the jet fighter, at the top we would subtract gravity, at the bottom we add, right? So it just so happens we're adding and subtracting exactly one weight, or 1W. This is really just a pretty much proportion problem. We have some mass in a horizontal circle going at some speed v at the end of a string of length L. So the radius it's going around is L. That's the length of the string. It says the tension is T. Now, if the speed is doubled, but everything else remains the same, what's the tension? Well, we know that tension would be mv squared over r, right? So if we keep everything constant and we double the speed, we have mass times now 2v squared over r, which is 4. 2 squared is 4, so we have 4 mv squared over r. So the tension actually becomes 4 times as much. Again, here we have pretty much just a proportional reasoning problem. We have two 1 kilogram point masses. And by the way, a point mass is something that you can consider the entire mass to be at one particular point. Like, let's say we had a car, and we had two cars, and we're finding the gravitational attraction between two cars. We could, in order to find the distance between them, we just say, okay, each car has all of its mass at the very center of the car. And so we assume that the entire mass is at some point. Much easier to deal with otherwise. Otherwise, we'd have to take, okay, the fender to fender and the masses of those fenders and the distance between the wheels and all kinds of stuff. So we just assume they're point masses to make life easier. So we have these two 1 kilogram point masses, some distance d away from each other, and they exert a gravitational attraction F on one another. And now we're going to add a kilogram to each mass, right? So what would be the gravitational attraction? Well, I had two 1 kilogram masses, now I have two 2 kilogram masses, right? So before we had 1 times 1 was 1, and now we have 2 times 2 is 4, right? So we've quadrupled the force, right? Because from 1 kilogram to 2 kilograms, we effectively doubled it, right? So if we doubled each mass and the masses are multiplied, they're squared, right? So we have 2 squared would be 4 times as much. If I were to triple each mass, so I made this 3 kilograms and the other one was 3 kilograms, I tripled them and then they're effectively squared, then it would be 3 squared is 9, right? So it would have been 9 times the force. But here we have doubling the masses, so we quadruple the force. So another proportional reasoning problem. We have these two masses, some distance d apart, and they have a gravitational attraction of F, and I want to make that 1/3 F, right? Well, you know, the law of gravitation, Newton's law of gravitation says the force is G m1 m2 over r squared, or in this case, d squared, right? So I want to make it so that the force is 1/3 of that, right? So when I square it, I need to end up with 1/3 d. So the one that we would have that does this once we square it is a, right? When I square, if I take the radical 3d and I square that, I would end up with 1/3 d, right? Which is exactly what we want to do to get 1/3 f. But run through that, write out the equation, you can plug these in, For 3D, like if I changed it to 3D, it would actually make it 1/9, right? It would make it 1/9 D. If I put in 1/3 the distance, it would actually be 9 times the force. If I made it 9 times the distance, it'd actually make it 1/81st of the force, right? Of the force. So you can put in these and see how it affects the force.